Here we're going to find the volume of the solid of revolution formed by rotating about the x-axis, the region bounded by the curve y equals x squared plus 1 and the curve y equals negative x plus 3, which happens to be a line. We're going to use a disk method. Step 1, find the limits of, in other words, the points of intersection to set up the limits of integration. You do that by setting the curves equal to each other, y equals y, and solving for x. So you have x squared plus 1 equals negative x plus 3. When you solve that, you factor x plus 2 times x minus 1 equals 0, and then you get your points of intersection, x equals negative 2 and x equals 1. Now you can find ordered pairs for each of these by just substituting each of the x values into either of the two given functions. And it doesn't matter which, because these are points of intersection, so they share the same y partners. So we do that and we get the ordered pair negative 2, 5 for the first point and 1, 2 for the second point. And that establishes our interval of integration, the integral from x equals negative 2 to x equals 1. Step 2, we're going to sketch this situation, this intersection of these two curves. Here's our y-axis and our x-axis. We've drawn the line negative y equals negative x plus 3, and the inverted parabola shifted 1 unit up, y equals x squared plus 1. We've drawn their points of intersection at the two ordered pairs, negative 2, 5 and 1, 2. And then we've noted down on the x-axis that the a value, the lower limit of integration, is going to be at negative 2, and the upper limit of integration is going to be at b equal 1. And you see we've drawn the little curly arrow to indicate that the axis of rotation is the x-axis. Now if you just look at this sketch and imagine this whole picture rotating about or revolving about the x-axis, it's sweeping out a solid and it's leaving a big hole in the middle. Do you see that big gap it's going to be leaving in the middle? It's sort of like a hole inside of a cup. So we're drawing, I'm here trying to draw that picture. Let me get the animation going. I'm trying to draw a three-dimensional rendition of what it would look like if we swept the image out in rotation. You see the thickness I'm putting inside of this cup? That's because the walls of the cup have thickness because of this region that's being rotated. Now I'm going to cut a slice out of this. This is my disc that I'm slicing out of the solid. You'll notice the disc is perpendicular to the axis of rotation that goes right through the center, but you'll also notice there's a hole in the middle of the disc because that area is empty. That makes this disc more of a washer, kind of like the washer you put on your bicycle tire. So, and it's arbitrarily located. That's why I call it an arbitrary disc. And now I'm going to try to get you to believe that the radius of this disc, we're only interested in the area of the face. So we're only interested in the radius where we have material, not the hole. So we're going to have our outer radius minus an inner radius. So let's speed this along. We have the axis of rotation going through the center, and then we have the lines that are going through. Remember, this is an extreme close-up, so even the curves look like straight lines here. So we have a line passing through the inner upper and inner outer, and then the outer upper and outer bottom, I should say. And this distance from the x-axis up to the first curve is called the inner radius. That's little r. It's represented by the curve y equals x squared plus 1 because that is the lower curve. And then the outer radius, its distance from the x-axis, the center, because that's the axis of rotation, that's called our outer radius, capital R, and it's represented by the upper function, negative x plus 3. So you see here we've established an inner function, little r, with x squared plus 1, and the outer function, capital R, with negative x plus 3. And we're going to use that when we determine the area of the face of this washer. See, this way we're not going to be accounting for the open region in the center. Okay, so we're going to step 3. Step 3 is finding the area of the arbitrarily located disc face. I call it a disc, it's a washer, whatever. So the area of this disc can be represented in a simplified picture, a bird's eye view of the washer. there's the center, the small radius, little r, the large radius, the outer radius, capital R. And with capital R, the outer radius being equal to the upper function, negative x plus 3, and little r equaling the inner function, the lower function, x squared plus 1. So area A is equal to the area of the outer radius circle minus the area of the inner radius circle. Okay, can you see that? All right, so that's A equals pi times capital R squared minus pi times little r squared, which is pi times parenthesis negative x plus 3 squared minus pi times parenthesis x squared plus 1 squared. Step 4, now find the volume now that we have the area of the face. Volume is equal to the integral from the lower limit, x equals negative 2 to positive 1 of the area in terms of x of the washer dx. I call it a washer, yeah. So it's equal to negative 2 to 1 of pi times negative x plus 3 squared minus pi times x squared plus 1 squared. That's the area that we got in step 3, dx. Now simplify inside the bracket. You get pi times 8 minus 6x minus x squared minus x to the 4th dx after you clean everything up. So that's pi times the antiderivative 8x minus 3x squared minus x cubed over 3 minus x to the 5th over 5 evaluated from x equals negative 2 to 1. And when you do all the arithmetic, you get 117 times pi over 5. So here I want you to notice that finding the area was probably one of the more complicated things you had to do, because you had to take into account that when you spun or revolved this region around the axis of rotation, you were leaving a big hole in the middle. So you had an outer radius and an inner radius, and you had to calculate the areas separately and take the outer radius area and then subtract the inner radius area.